Okay, so here is Bernie the chicken. The total distance is 12 feet. So this is 12 feet. And Bernie's trying to make it all the way across. Leg one. Bernie's going half the distance there. So how far did Bernie travel in leg one? 6 feet. So on my little tabulation over here, here is Bernie. Waddle, 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 waddle. There we go. How much is left? 6 feet. So now we're on to leg two. If there's 6 feet left and Bernie travels half of that distance, how far does he travel this time? 3 feet. So waddle, 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 waddle. How much is left?
3.
Okay, so there's 3 feet left. So now we're on to leg three. Bernie travels half of that distance. What's half of 3?
1.5.
So in this leg, Bernie travels 1.5 feet. Waddle, 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 waddle. There's Bernie. Okay, so now we're getting shorter distances. There's 1.5 feet left. Leg 4, Bernie goes halfway there. How far did Bernie travel? If you travel 0.75 feet, that means there is 0.75 feet left. Okay, now we're on to leg 5. Leg 5, there's 0.75 feet left. You're going halfway there. How far is Bernie going to travel this time? 0.375. So waddle, 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 halfway there. Bernie's getting very close. Should only take a few more times maybe. So now 0.375 feet away. You're going halfway there. What's half of 0.375? 0.1875. So waddle, 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 halfway there. And there we are at leg 6. How many more times are you going to have to do this for Bernie to get there? Is Bernie ever going to make it?
No, he's going to get hit by a car. How is he moving such a small Bernie will make it, man.
So always halfway there, always halfway there. Even if it's a really tiny little distance, you're only making it half of the way there, so there's going to be a little bit of distance left over. So this is what's happening with an infinite series. Eventually, what we say as mathematicians is eventually, if you could do this not 100 times, not 1,000 times, but in theory, if you could do it an infinite number of times, we're going to say eventually you're going to make it there. So that's one of the concepts we have for today. Okay, so here's the example. Question number 2. We'll come back to these numbers in a little bit. Write a rule for how far Bernie walks on the nth leg of his journey. So a sub n equals, this is a geometric sequence, right? Because we keep multiplying by the same number every time. We keep multiplying by 1/2. It's supposed to be a sub 1 times the common ratio to the n minus 1 power. What is our first term here? 6. What's the common ratio? 1/2. You could have put 0.5 as well. So here is our formula. So if I want to know how far does Bernie walk on the 7th leg, I don't have to go through all these other ones to get there. I can plug 7 in for n, run it through this equation, and get that actual distance. How far is Bernie traveling on the 20th? Plug 20 in for n, run it through there, and I see how far he's traveling on that 20th trip. Question number 3 says, let's look at Bernie's overall progress. Find the total distance he's walked by the end of each leg of his journey and plot these points on the graph. Okay, so leg 0, he's traveled 0. Nothing's happened yet. But at the end of leg 1, how far has Bernie traveled?
6.
So 1, 6. Okay, at the end of leg 2, so leg 1, 6 feet. Leg 2, we've already traveled 6 feet plus how much more? 3 feet. So how far has he traveled? 9 feet. So 2, 9. Leg 3, we've already traveled those 9 feet plus how much more? 1.5. So how far entirely? 10.5. Okay. So the difference between these is changing. Now to leg 4, we're going to take that 10.5 and add how much more to it? 0.75. So 10.5 plus 0.75 would be 11.25. So estimate 11.25 right there. Leg 5, how much more do we add to that? So plus 0.375. So that's just barely over 11.5. So a little bit over halfway there. Leg 6, we're going to take that number and add in an additional 0.1875 because that's how far it traveled on this leg. And isn't that even a little bit closer to 12? Just a little bit higher. What do you think is going to happen as we keep going farther and farther to the right?
It's going to get closer and closer, but it will never touch it.
A little bit closer, a little bit closer, a little bit closer. But the numbers we're adding on are so small, it's not taking it up very quick. It's going to be a gradual, a slow climb up to 12. So question 4, on which leg of his journey will he completely cross the road?
Infinite.
So assuming that Bernie could live forever.
Yeah. Bernie can't. He lives on paper. He's stuck on the third.
Poor Bernie. Chickens can kind of fly.
No. They can fly. What? Chickens can't fly.
Kind of.
If Bernie can't walk across the road, chickens can. They can.
So in theory, if possible, if we can do this an infinite number of times, then Bernie could get there, but that's never going to happen. So poor Bernie's never going to cross this road. Now, question number 5, let's look at this one carefully. It says, if leg 1 takes him 64 seconds, so leg 1 was what distance? 6 feet. So here's the entire 12 feet. So if leg 1 takes him 64 seconds, and he doesn't stop, we don't call this leg 1 and move on to leg 2. So leg 1 takes him 64 seconds, and then he continues walking at that same pace. Will he be able to cross the road then?
Yeah.
Yes. So slightly different scenario. It's not going halfway and then halfway and then halfway. It's 64 seconds to go 6 feet. Well, then how long is it going to take to cross the road entirely? 128 seconds. It's 2 minutes, 8 seconds. So this question number 5 is actually a linear or an arithmetic sequence because it's a common difference. Leg 1, 64 seconds. Leg 2, 64 seconds. Slightly different. The way the problem was phrased was different. Leg 1, then times 0.5 to get to leg 2, times 0.5 to get to leg 3, and so forth. And then we're going to cross off this question 6. All right, turn the page. In this context, when you see the letter S, what is that standing for? Sum. So, and then there's a little subscript down here. In this case, it's not a number. It's not S sub n. It's not S sub 20. It's S sub infinity. So this mythical or idealistic infinity. So what if you found the sum of this infinite series and it keeps on going? So the sum of an infinite might look like this, where n equals 1 to infinity of some geometric series. It's geometric. There's a first term times the ratio to the n minus 1 power. Can we actually find the sum of a series like this? The answer is yes, as long as it meets a certain condition. This is not going to exist. It does not exist if the absolute value of r is greater than or equal to 1. So if r is bigger than positive 1 or if r is less than negative 1, we're going to have issues with this. We would say the series does not converge. The series diverges. Converge means it's getting closer to a specific number. Diverge means it's not getting closer to anything at all. And the reason for that is if your common ratio is a big number, then like in the last one, instead of 1 or 0.5, what if your common ratio was 2? So the first time he would have gone 6 feet, and then he would have gone 12, and then 24, and then 48, and then 96, and so forth. And you add all those together, is that getting closer to any number? No, it just keeps getting bigger and bigger without bound, so that it is not going to converge to any specific number. Same thing, if r is less than a negative 1, what would happen there? It would oscillate actually back and forth. You get a positive value, then a negative value, then a positive value, then a negative value, because when you multiply by a positive times a negative, you get a negative. And then a negative times that negative ratio gets you back to the positive again. So it's kind of a weird one. Ideally, though, the common ratio is between 0 and 1. It is positive and it's less than 1. And then the series is going to sum up to this nice little formula. A sub 1 over 1 minus r. Very nice formula. Yesterday I talked about the formulas. I met with the rest of the pre-calc group, and you will be given formulas for your quiz as well as your test. Not just the the long one with the sum of the finite geometric series that look like this. You're going to be given the arithmetic series as well as how to find the common difference, common ratio, and so forth. So it's not a memorizing test. It's can you use these formulas that you've been provided with. So big task today. Can you find the sum of an infinite series? It might look like this. And then we have this nice simple formula for it. All right, let's jump into some examples. Example 1, part A. First of all, without a calculator, then we'll go to the calculator. So it says, find the sum that k goes from 1 to infinity of 3 times 0.25 k to the negative 1. I know this is a geometric series because our first term, a sub 1, is equal to 3. This 0.25 is our ratio. It's our common ratio raised to the k minus 1. It looks exactly like one of those geometric sequences that we talked about. To find this series, I could plug 1 in for k, find the number. Then plug 2 in for k, find the number. Plug in 3, plug in 4, plug in 5. And then in theory, I would do it an infinite number of times. After a while, though, when I plug in a huge number for this, and I take 0.25 to a huge power, that's going to be a tiny little number times 3, so it doesn't move the value very much at all. So with this one, we're going to say, all right, how about we just try this formula? A sub 1 over 1 minus r. What is the first term in this series? 3. I see it's in that general form. 3 is out front. And just to be clear, if I were to plug 1 in for k, 1 minus 1 is 0. 0.25 to the 0 is just 1. Anything to the 0 is 1. So then 1 times the 3 does give us that leadoff term of a 3. So a sub 1 over 1 minus r. What is our common ratio this time? 0.25. So we have 3 over 1 minus 0.25. That's 3 over, I know this is 0.75. 0.75 as a fraction would be 3/4. I don't like seeing a number divided by a fraction, so I could divide by 3/4. I think that's harder to understand. Instead, maybe multiply by 4/3. That gets that out of the denominator. And this makes more sense to me. 3 times 4 is 12. 12 divided by 3 is 4. Now, about this problem, I want you to go into your calculator and let's check this with your sigma. So you have math, the sigma one, scroll to the sigma, and we can't plug in infinity as a number on our calculator. That's not possible. But what could we plug in instead of infinity?
A really, really big number.
A really, really big number, right? So how big do we have to go? I'm going to have you try, just go to 15 to begin with. So plug this in and have the upper bound go to 15 instead of infinity. So a little practice in using that. Make sure you remember how to use the summation.
Do you mean 15 a number or click a button 15 times?
Just type the number 15 up there.
Oh.
So if you go from 1 to 15.
I have a pass. Don't worry, guys. I was like,
So if you go from 1 to 15, you get a sum of that series, right? Like it gives you an actual answer. 15 wasn't a huge number. 15 is far from infinity, but what value did it give you? 3.99, something pretty close to 4. Let's try a bigger number like 150. So if you hit your up arrow, all you need to do is on that sigma change that 15 into a 150. Is it too big of a computation for it? Maybe it takes a little while longer, but the calculator eventually just gives up and says, okay, this is essentially 4. Let's call it 4. And that's just going 150 times. 150 is far from infinity, right? But eventually it gets so close it says, yeah, this is 4. So I can check this on my calculator with sigma, know how to use these formulas because, again, sometimes the calculator is not going to be able to do the problem in a certain context. If you ever get to the point where your calculator is like frozen and it's like it's stuck in a loop, if you hit second on, which is normally how you turn it off, it'll stop the loop. Then you have access to your calculator again. Otherwise, it could be like stuck in a loop for a long time.
Why does it give you 4? 1,500.
because it's so close to 4 and how many decimal places you get, it's like saying, okay, it's 4.
It's basically rounding.
Okay, there's this poor lettering system here. Let's go to this letter B on the right, the one I have in pink. We want to find the sum of this infinite series. It's I instead of k, not a big deal. I goes from 1 to infinity, 3 times 1.25 I to the I minus 1 power. Is it an infinite series? Yes. Is it geometric? We have like an a sub 1. We have a common ratio. So can you try to use that formula we just used, this a sub 1 over 1 minus r? Can you use that formula to find the sum of this series?
Sure. I don't know. Oh, wait, the sum? Yeah, you're right. Yeah, thanks.
I didn't know it. This one doesn't work.
Zach and I, man, can do it.
Wait. Wait.
Good question.
How do you know what number to count the sum?
How
How do you know what number to count the sum?
So the first term, 3. So it's a sub 1 times r to the n minus 1. When it's a geometric sequence, it's always,
So just pick any number?
no, it's always, it's going to be this number. Like if I plug 1 in for I, 1 minus 1 is 0, 1.25 to the 0 is 1, 1 times 3. My first term is 3.
So put on the top of this summation. Is that what? I'm so lost.
Okay,
It's not that bad.
in this problem, when I use this formula, if I try to plug this into my calculator, if I put some other number other than infinity, like 20, 30, 40, whatever, that is just like trial and error. We're going to try to use the formula. This is one of the ones where I'm going to try to use this formula. The first term is 3. The common ratio is 1.25. So a sub 1 divided by 1 minus r. And I got negative 12. Does that answer make any sense? If the first number is 3, the common ratio is positive 1.25. That means your second term is going to be positive 1.25 times bigger than this. Then the next term is bigger. The next term is more positive. Then the next term is bigger. You're adding all these bigger positive numbers. Is it at all possible you could end up with a negative result? No. And remember, in this we said in order to use this formula, the ratio has to be less than or less than 1. It doesn't work if the ratio is greater than 1. So once you see that this common ratio is bigger than 1, this sum does not exist. If you did the trial and error method, like with the number up top, you could go from 1 to 20. You go from 1 to 20 and get an answer. 1 to 40, you're getting a much bigger answer. 1 to 1,000, you're getting a huge answer. Eventually, it's going to have an overflow because it's not converging to anything. Letter B, this pink letter B does not exist. Okay, so you've got to keep that in mind. Check those common ratios. Otherwise, you'll get an answer that just doesn't make sense. Okay, to this yellow letter B. Trying to find the sum of this series. First check, is it geometric? We have a first term times a ratio. It's to the k power, not k minus 1. That's a little bit different. So we're going to have to pay attention, like what does this k rather than k minus 1 do? And then maybe even a bigger difference, it's k equals 0 to that. This bottom number isn't always 1. We talk about the first term. It might be better termed as like the leadoff term because sometimes your first term isn't a1. It might be like a sub 0 in this case. Or if it's going from 5 to infinity, a sub 5 would be your leadoff term. So in this one, yes, it's geometric. It's an infinite geometric because that's our upper bound. So the sum is the formula. First term divided by 1 minus the common ratio. The ratio this time is 1/3. Is that an acceptable ratio to have in this case? because it's less than 1. The first term, is it 5? Maybe I'm not sure. If I plug 0 in for k to check, what is 1/3 to the 0? It's still 1. 1 times 5? 5. So 5 is, in fact, our first term. Like, this is like a little trade-off. If it was k equals 1, then we'd want that to be k minus 1. But if this bottom number is 0, then we want it to be k. So we have this, not terribly difficult calculations here. It's 5 over 2/3. Multiply the denominator by 3 over 2. Multiply the numerator by 3 over 2. We get 15 over 2, which would be 7.5. So your first term was 5. Your next term is 1/3 as big as that, and then 1/3 of that, and so forth. Keep adding all those on there, and it's going to converge on 7.5. This is a pre-calculus topic known as the limit. As n, or as k approaches infinity, the number of terms we have approaches infinity, it is converging on this 7.5.
Is our test going to be all calculator?
We'll talk about that on Monday. So Wednesday is the quiz, and you'll have the formula sheet given, but we'll talk about more details on Monday. Okay, letter D. Letter D. Is this one possible?
No.
It's possible. It's not too definitive.
I don't want to call it a trick question, but pay attention to the details. Look at the pink and look at the blue. They're almost the same equation, right? What is the subtle little difference?
It's 120.
Only to 20. So even though this number is bigger than 1, we still can find the sum of it because we're only finding the first 20 terms. So we do have a formula for this. S sub n, this is one of the more difficult ones, is a sub 1 times 1 minus r to the n over 1 minus r. Again, this will be provided. Can you interpret what this means, and can you make it specific to this problem? We have s sub n. What is n equal to in this one? 20, because we have the first 20 terms. S sub 20 is equal to, what is a sub 1? 3, parentheses, 1 minus 1.25 to the 20th over 1 minus 1.25. I'm just taking this formula, plugging in the specific numbers from our example. Go ahead and calculate it. So we have the sum of these first 20 terms. It should converge to something. Hopefully it's not too big. Sometimes you do stuff on the calculator and it gives you what's called an overflow error. The calculator can't comprehend that big of a number. Hopefully this one is in range, and I think it is. 1,028. 0.834.
It's about that.
All right, go ahead and compare your letter D if you need some time. We're going to skip number 2 and go down to number 3 here in just a moment. All right, perfect name for a person who's baking. It says, once a week, Mrs. Baker makes sugar cookies. The first week she makes the recipe, she uses the full 2 cups of sugar that are called for in the recipe. Each week after that, she reduces the amount by 1/3. How much sugar does she use for the cookies on the 5th week? So she's making the regular recipe in the first week. Then she decided, you know what? I'm going to make them next week, but with less sugar. She doesn't think sugar is healthy, so she's trying to make these cookies with less sugar in them. The key phrase here that is kind of difficult is where it says she reduces the amount of sugar by 1/3. That doesn't mean she's using 1/3 of the amount. She is reducing it by 1/3. So for example, if you have 30 of something and you reduce it by 1/3, then how many do you have? Reduced by 1/3, you end up with 20. What is 1/3 of 30? 10. So 30 reduced by, subtracted by 1/3 of that gives you 20. So that is reducing it by 1/3. So if you are reducing it by 1/3, what fraction are you keeping? 2/3. So this phrase that I have underlined where it says she reduces the amount by 1/3 means she is keeping 2/3. That's the same thing that it's saying. 2/3 is what we want to use in this one. The way it was phrased again, a little tricky, but that's what it means. So how are we going to answer this first question? How much sugar does she use on the 5th week? I know on the 1st week she's using a full 2 cups. Then she multiplies that by 2/3 to get the 2nd week. Multiplies that by 2/3 to get the following week, and so forth and so forth. Let's go there directly. This is a geometric sequence, right? Because you're multiplying by a common ratio every time. A sub 1 times r to the n minus 1. Let's be specific on this one. A sub 5, the 5th term, is equal to, what are we going to put in there for a sub 1? 2 times what's our common ratio? This is the 2/3. We're keeping 2/3 of it to the 5 minus 1, which should be 4. So go ahead and multiply it out. Let's see how many cups she is using on this 5th week. We expect it to be something less. The 1st week was 2 cups. Then it was less, then it was less, then it was less. By the 5th week, how many cups of sugar is she actually using?
0.395.
So again, maybe the goal here is I'm trying to use less sugar. The 1st week they tasted great, the regular amount of sugar. By week 5, maybe she's hoping they don't notice the subtle difference every week because she's only using 0.395 cups of sugar. Or she's healthy. Question B. How much sugar does she use in total baking cookies for half a year? So question A was, how much does she use just in the 5th week? If I wanted to know in question A, like, how much does she use in total by the 5th week, I'd have to add week 1 plus week 2 plus week 3 plus week 4 plus week 5 to see how much total she has used. Well, in question B, it's saying how much total has she used in half a year? How often does she make these cookies? Every week. So in half a year, how many times did she make the cookies? 26? 52 weeks in a year. Half of that is 26.
How do you know that? I thought there was 52 weeks in the year. Yeah, how do you know?
365 days in a year. Did you know that one?
I know how many days. Yeah, I didn't know how many weeks. Yeah, I just knew days.
Oh my. Okay. This is a sum. Again, we're adding all these up. So the sum of these 26 weeks is equal to, let me scroll back up here. Here is the formula. This is the sum for a finite geometric series. It's not infinite this time. We're doing 26 weeks, not an infinite number of weeks. What is a sub 1 in the context of our problem?
Week 1. No.
How much?
5. No. What?
One more try.
In the first
It's
week,
the 2. It's the 2
in the
cups.
first week, how many cups of sugar?
2.
2. So a sub 1 is 2. What is the r value? 2/3. And then what is n going to be? 26. So there's 26 weeks in half of a year. And by the 26th week, she's not using very much sugar at all. So the difference between the 25th week and the 26th week probably isn't very much. And from 26 to 27 is even less. So these numbers you're adding are very small. We should be converging on something here. After 26 weeks, how many cups of sugar have you used entirely? Normally I ask for 3 decimal places. Let's go 4. So there's no way this is Mrs. Baker is getting that precise and that she has a measurement that gets 0.0001 cups of sugar. But in theory, that's what's happening in this situation. So this is how much she has used in half of a year. question C. It gives us a little bit more information. We have to use some conversions here. It says sugar can be bought in 1 pound, 4 pound, 10 pound, or 25 pound bags. Mrs. Baker wants to buy one of those bags. She's going to the grocery store just once. She wants to buy enough, but she doesn't want to buy more than she needs. So which of those should we buy? It says there are approximately 2 1/4 cups of sugar in 1 pound. If she plans to keep up this habit indefinitely, what size bag does she need? So this word indefinitely, what's a synonym for us in terms of math?
Forever.
Infinite. Infinite would be like our math word there. She's doing this an infinite number of times. It's a geometric series, an infinite number of times. The formula for the sum of an infinite series is this one, this a sub 1 over 1 minus r. So the sum of this series is equal to, what is a sub 1 in this case?
2.
2 over 1 minus, what's the ratio? 2/3. So that's 2 over 1/3. If I multiply numerator and denominator by 3, it cancels out the denominator. The numerator, we get 6 cups. So letter B, just above it, we asked how many cups would you have for half of a year? 5.9998. Well, if you did this an infinite number of times for the rest of her life and then well beyond when she's living, you would only need 6 cups because you're adding such small values at a certain point. Now you have to figure out 6 cups. Well, how many pounds is that equal to? Let's see. 2 1/4 cups is equal to 1 pound. 2 pounds would be how many cups? 4 1/2, just double it. Okay, and then let's double this again. 4 pounds, because there's a 4 pound bag of sugar, would be how many cups? Double 4 1/2? 9. So in the 4 pound bag of sugar, she'd have 9 cups of sugar. Does she need that much? No. Was 1 pound bag enough? No. So what is she going to get? 4 pound bag, because that has enough without going any more than we need to.